Tonight, we're going to explore a truth that defies everything your instincts tell you about stability. You look at the world around you, the ground beneath your feet, the stars above your head, the atoms in your body, and you assume they are fixed, permanent, stable. But when scientists measure the fabric of reality itself, they discover something unsettling. Everything is moving away from everything else. The space between galaxies isn't just stretching, it's accelerating. The forces pulling the universe apart are getting stronger every single second. And by the end of tonight, you're going to understand why the universe is expanding for a reason, what dark energy actually does, why this moment in cosmic history is more fragile than you can possibly imagine, and why the expansion of space might be the most terrifying force in existence. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The farthest stars you can see are maybe 15,000 light years away. That sounds far. It is far by human standards. But the observable universe spans 93 billion light years in diameter. You're seeing less than a fraction of a percent of what's out there, and even those stars you see, they aren't staying put, they are being carried away. The silence of the night sky isn't peace, it's the sound of everything drifting apart. To understand just how fast this is happening, you need to forget everything you know about speed. A car on a highway moves at 100 kilometers an hour. A jet aircraft breaks the sound barrier at about 1,200 kilometers an hour. The Earth orbits the Sun at 107,000 kilometers an hour. Those numbers are impressive, but they are nothing compared to what the universe is doing to the space between galaxies. The Hubble constant, named after Edwin Hubble, who first discovered the expansion in 1929, tells us that for every megaparsec of distance, that's about 3.26 million light years, space expands at roughly 70 kilometers per second. That doesn't sound terrifying until you do the math. A galaxy 100 megaparsecs away isn't moving at 70 kilometers per second. It's moving at 7,000 kilometers per second. That's 2% of the speed of light. A galaxy 2,000 megaparsecs away, and there are galaxies much farther than that, is moving at 140,000 kilometers per second, nearly half the speed of light. And at the edge of the observable universe, galaxies are receding faster than light itself, not because they are moving through space, but because space itself is stretching. The fabric of reality is expanding faster than the fastest possible signal. Now, here's where most explanations get it wrong. People imagine the Big Bang as a bomb that threw matter outward into a pre-existing empty space. That is not what happened. The Big Bang was not an explosion in space. It was the explosion of space. There was no center. There was no edge. The expansion doesn't have a point of origin that you could travel back to. Every point in the universe is moving away from every other point. This means if you were standing on a galaxy 10 billion light years away, you would see exactly the same thing we see from Earth. All galaxies rushing away from you in every direction. You would think you were the center. And you would be just as wrong as we are, because there is no center. The universe has no privileged location. The expansion is uniform, isotropic, and relentless, and for decades physicists assumed that gravity would slow this expansion down, that the mutual attraction of all the matter in the universe would act like a cosmic brake. The universe would expand more and more slowly, maybe eventually stop and reverse into a big... That was the reasonable assumption. That was what every intuition predicted. And that assumption turned out to be catastrophically wrong. In 1998, two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, were measuring distant type Ia supernovae. These are exploding white dwarf stars that always have the same intrinsic brightness. That makes them perfect cosmic mile markers. You measure how bright they appear, you know how far away they are. You measure their redshift, you know how fast they are moving away. The teams expected to see the expansion slowing down, Instead, they saw the opposite. The distant supernovae were dimmer than they should have been. That meant they were farther away than expected. That meant the expansion of the universe was not slowing down. It was speeding up. Something was pushing the universe apart. Something that overcame the gravity of every star, every planet, every black hole, every dark matter. Something that makes up about 68% of the total energy density of the cosmos. We call it dark energy. But that name is a confession of ignorance. We don't know what it is. We only know what it does. It creates a repulsive gravitational effect. It lives in empty space itself. And the more space expands, the more dark energy there is. The more dark energy, the faster the expansion. The faster the expansion, the more space is created. It's a feedback loop, a runaway process, and it has already determined the ultimate fate of everything. Let's stop here and really feel the weight of that discovery. Before 1998, the universe had a chance at a dramatic ending. The big crunch. Everything reverses. Galaxies collapse back together. The fabric of space-time crumples into a singularity. Maybe another Big Bang follows. A cycle. A rebirth. That possibility is now gone. The acceleration is too strong. The universe will never stop expanding. It will never reverse. It will and as it expands, it gets colder, emptier, darker. This is the heat death we discussed in previous episodes, but now you understand the engine driving it. Dark energy is the engine. It is not a mysterious fluid that might change its behavior. The data from the Planck satellite, from the Dark Energy Survey, from the James Webb Space Telescope's observations of ancient galaxies, all point to the same conclusion. Dark energy is consistent with a cosmological constant, a term that Albert Einstein first added to his equations in 1917 and then called his biggest mistake. He added it to make the universe static, because static was the fashion. When Hubble proved the universe was expanding, Einstein removed the constant. He called it a blunder. But in 1998, the blunder came back. The cosmological constant is real. It is the energy of empty space, and its value, measured in grams per cubic centimeter, is about 10 to the minus 29. That number is absurd, but multiplied by the volume of the universe, it dominates everything. Now we need to talk about what this acceleration actually feels like. You don't feel it because gravity is still stronger than dark energy on small scales. The Milky Way and Andromeda are not being pushed apart. They are on a collision course. The gravity of our local group overcomes the expansion. The solar system is held together by the sun's gravity. The Earth is held by its own. Your body is held by electromagnetic forces. Dark energy only wins on the largest scales, scales of hundreds of millions of light years and above. But here is the terrifying part. The acceleration is constant. Gravity falls off with distance. Dark energy does not. Over extremely long time scales, trillions of years, the expansion will eventually overcome gravity even on smaller scales. Galaxies will be torn apart. Stars will drift away from each other. Planets will be unbound from their atoms themselves might eventually be ripped apart if the acceleration continues to increase. That scenario is called the Big Rip, and it is not the leading theory because dark energy seems constant, not growing. But we cannot rule out the possibility that dark energy is not constant, that it is a phantom energy that grows stronger over time. If that is true, the end comes much faster. Not in trillions of years, but in tens of billions. The Milky Way would be torn apart 60 million years before the final end. The Earth would explode 30 minutes before the end. And in the final seconds, molecules, atoms, and finally atomic nuclei would be ripped apart. That is the nightmare scenario. And we don't have enough data to rule it out. But let's return to the present, to the science we are certain about. The expansion of the universe is accelerating, and that acceleration has already sealed the fate of everything beyond our local group of galaxies. Right now, there are about 2 trillion galaxies in the observable. But many of them are already beyond our reach, not because we can't see them. We can. Their light has been traveling for billions of years. But because of the acceleration, any galaxy currently more than about 18 billion light-years away is permanently unreachable. Even if we built a spaceship that traveled at the speed of light, we could never get there. The space between us is expanding faster than light speed, and this is getting worse. As time goes on, more galaxies cross that horizon. In 100 billion years, all galaxies outside the local group will have receded so far that their light will never reach us. They will vanish from the observable universe. A future astronomer looking at the night sky will see only the stars of the Milky Way, and a few faint smudges from Andromeda and the Triangulum galaxy. That astronomer will have no evidence of the Big Bang, no cosmic microwave background, because that will have red-shifted into undetectable radiation. No Hubble expansion, because everything visible will be gravitationally bound. That astronomer might conclude that the universe is static, eternal, and contains only one galaxy. That astronomer would be wrong, but they would have no way to know. The acceleration of the universe is not just pushing galaxies apart, it is erasing the evidence of our cosmic origins. There is a deep philosophical terror embedded in this physics. We exist at a very specific time in cosmic history, early enough that we can still see the afterglow of the Big Bang, early enough that galaxies are still visible in the billions, but late enough that the acceleration has already begun its quiet work. We are living in the only epoch where the expansion is detectable but not yet devastating. If we had evolved 100 billion years later, the universe would look empty. We would have no proof of the Big Bang, no data to derive dark energy. We would be alone in a bubble of stars, forever ignorant of the larger cosmos. This is called the Golden Age of... We are in it right now, and it will not last. Every year that passes, the cosmic horizon expands by a tiny amount, not outward but inward. The volume of space we can ever reach shrinks. The number of galaxies we can ever visit decreases. The universe is not just expanding, it is leaving us behind, and there is nothing we can do about it. Dark energy is not a force we can fight. It is a property of space itself. To stop the acceleration, you would have to change the laws of physics, which means for all practical purposes, the universe is slowly going dark around us. The stars are not dying. They're fleeing, and the void between us and them is growing at a rate that mocks every human concept of distance. Let's put a number on this. The Hubble constant is about 70 kilometers per second per megaparsec. That means for every 3.26 million light-years you look out, things are receding an additional 70 kilometers. At the edge of the local group, about 10 million light-years away, the expansion is negligible compared to gravity. But at 100 million light-years, the recession speed is about 2,000 kilometers per second. At 1 billion light-years, it's 20,000 kilometers per second. That's 6.7% of light speed. At 10 million light-years, it's 200,000 kilometers per second. That's 67% of light speed. And at the cosmic horizon of about 14 billion light-years, the recession speed exactly equals light speed. Anything beyond that horizon is forever inaccessible. But here's the kicker. That horizon is not static. Because the expansion is accelerating, the horizon is shrinking, not in physical size, but in terms of the moving distance we can ever reach. Today, the reachable universe, the volume where light from us could someday arrive, is about 16 billion light-years in radius. In 1 trillion years, that reachable radius will be the size of the local light-years, a reduction by a factor of 1,000. The universe we can influence is collapsing around us, not because space is contracting, but because the expansion is taking everything away faster than we can ever catch up. This leads to a question that keeps cosmologists awake at night. Is dark energy really constant? Because if it is constant, the future is the heat death. Cold, dark, silent. But if dark energy is not constant, if it is a dynamic field like the Higgs field or the inflaton field, then anything is possible. It could get stronger. It could get weaker. It could even reverse, turning into an attractive force that pulls the universe back into a crunch. We have no evidence that it will do any of these things, but we also have no fundamental theory that says it must be constant. The cosmological constant is a number that appears in Einstein's equations. It is a free parameter. It can be any value. The fact that it has the specific value we measure, 10 to the minus 29 grams per cubic centimeter, is one of the great mysteries of physics. This is the cosmological constant problem. When quantum field theory tries to calculate the energy of empty space, it gets a number that is 10 to the 120 times larger than what we observe. That is a 1 followed by 120 zeros. It is the worst prediction in the history of physics, and it tells us that we are missing something fundamental, something about the relationship between quantum mechanics and gravity, something about the nature of nothingness itself. For the next section of tonight's journey, we need to talk about the actual evidence that changed our understanding of the universe. The supernovae that revealed acceleration were not just any supernovae. They were type Ia, which occur when a white dwarf star in a binary system steals so much mass from its companion that it exceeds the Chandrasekhar limit, about 1.4 times the reaction. The star detonates. For a few weeks, outshines the galaxy. And here's the key. All type Ia supernovae have nearly the same peak brightness. The physics of the Chandrasekhar limit ensures that the mass at ignition is almost always the same, so you can use them as standard candles. Measure how bright they appear, and you know their distance. Measure their redshift, and you know their recession speed. Plot distance versus redshift, and you get the expansion history of the universe. In 1998, the plot showed that distant supernovae were about 25% dimmer than expected in a universe without dark energy. That dimming meant they were farther away. That meant the expansion had been slower in the past and is faster now. The universe is accelerating. Saul Perlmutter, Brian Schmidt, and Adam Rees won the 2011 Nobel Prize in Physics for this discovery. But the story didn't end. The supernova data has been confirmed by 3 independent lines of evidence: the cosmic microwave background, the large-scale structure of galaxies, and the weak lensing of distant galaxies. All of them point to a universe that is about 68% dark energy, 27% dark matter, and only 5% ordinary matter. Everything we have ever seen, every star, every planet, every person, is less than 5% of the universe. The rest is invisible. And most of that invisible stuff is pushing the cosmos apart. Now, let's address a common misconception. Some people hear dark energy and think it's like a bomb, a hidden explosive that will suddenly tear everything apart. That's not accurate. Dark energy is not localized. It is not a field with lumps and bumps. It is smooth. It fills space uniformly. Its repulsive effect is tiny on small scales. The gravity of a single grain of sand overcomes the repulsion of dark energy across the entire. Dark energy only dominates when you have vast stretches of nearly empty space. The voids between galaxy clusters. The voids between superclusters. It is in those voids that dark energy has its greatest leverage. And because the voids are growing as the universe expands, dark energy's influence grows. This is why the acceleration is not a recent phenomenon. It began about 5 billion years ago, when the universe was about 9 billion years old. Before that, the universe was denser, and gravity dominated. The expansion was decelerating. The transition from deceleration to acceleration happened when the density of matter dropped below the density of dark energy. That crossing is one of the most important moments in cosmic history. It marks the point where the universe stopped fighting the expansion and started surrendering to it. We are living on the other side of that transition. The universe has already lost. The acceleration will continue forever. There is no force in the universe that can We need to take a step back and appreciate the scale of what we're discussing. The expansion of the universe is not something you can see with your eyes. The stars in the Milky Way are not flying apart. The Andromeda Galaxy is moving toward us, not away. The expansion only becomes visible when you look at galaxies that are far enough that the gravitational bonds between them are negligible. That distance is about 100 million light-years. Beyond that, the expansion dominates. But here's the weird part. The expansion of space also affects the wavelength of light. As a photon travels through expanding space, its wavelength stretches. This is the cosmological redshift. It is not the Doppler effect. The Doppler effect happens when a source moves through space. Cosmological redshift happens when space itself expands. The photon loses energy not because it's pushing against anything, but because the metric of space-time is changing. This means the cosmic microwave background photons we detect today started their journey when the universe was 3000 Kelvin. Now they are 2.7 Kelvin. They have lost 99.9% of their energy. That energy hasn't gone anywhere. It has been diluted by the expansion, and that dilution is accelerating. In the distant future, the CMB will be so cold and so redshifted that it will be indistinguishable from pure noise. The expansion of the universe is not just moving galaxies. It is cooling the afterglow of creation itself. Let's talk about the ultimate fate. If dark energy remains constant, the universe will expand forever. Galaxies will exhaust their gas and stop forming stars. Stars will burn out and become white dwarfs, neutron stars, or black holes. Over trillions of years, those stellar remnants will cool to near absolute zero. Over quadrillions of years, the orbits of dead stars will decay due to gravitational radiation, flinging most remnants out of their... Over googles of years, even black holes will evaporate via Hawking radiation. The universe will become a cold, dark, thin gas of elementary particles and low-energy photons. The temperature will approach absolute zero from above, never quite reaching it but getting arbitrarily close. This is the heat death, and it is the most likely outcome according to current data. But there is another possibility that we cannot yet rule out. Dark energy might change. It might get stronger. If it does, the expansion will accelerate faster and faster, eventually overwhelming all gravitational and electromagnetic forces. This is the Big Rip. In a Big Rip scenario, the universe ends not in cold silence but in violent disassembly. First, galaxy clusters are torn apart, then galaxies, then solar systems, then planets, then molecules, then atoms, then atomic nuclei. In the final second, the fabric of space-time itself is... We don't know which scenario is correct because we don't know the equation of state of dark energy. The equation of state relates the pressure of dark energy to its density. For a cosmological constant, the equation of state is exactly -1. For dynamic dark energy, it could be slightly less or slightly more. Current measurements from Planck and the Dark Energy Survey constrain it to -1.03 plus or -0.1. That range includes both the heat death and the Big Rip. We need better data. We need the next generation of dark energy experiments, the Euclid mission, the Roman Space Telescope, the Dark Energy Spectroscopic Instrument. They will measure the expansion history with 10 times better precision, and they might tell us whether the universe will fade or rip. But there is a third possibility, one that is rarely discussed in popular science. It is possible that dark energy is not constant, but that it is coupled to something else. Something like dark. If dark energy and dark matter interact, the expansion history could be radically different. Energy could flow from dark energy to dark matter, or vice versa. This could cause the acceleration to slow down, stop, or even reverse. There are models where the universe undergoes cycles of acceleration and deceleration, where dark energy decays into particles that then gravitate, pulling the universe back together. These models are speculative. There is no evidence for them. But they are not ruled out, and they highlight our ignorance. We have measured the expansion history of the universe back to about 1 billion years after the Big Bang, but we don't understand the physics driving it. We have a good measurement of the current dark energy density. We have a good measurement of the current expansion rate, but we don't have a fundamental theory. The cosmological constant problem remains unsolved. The nature of dark energy remains unknown, and the fate of the universe remains uncertain. This is not a failure of science. This is the frontier. This is where the excitement is. We are living through a revolution in cosmology as profound as the Copernican revolution. We have learned that we are not the center of the solar system, not the center of the galaxy, not the center of the universe. Now we are learning that the universe itself is not static, not eternal, not even slowly winding down. It is accelerating. And we don't know why. Let's move to the most disturbing implication of accelerating expansion: the eventual isolation of all civilizations. Imagine a civilization that arises in the universe 1 trillion years from now. Not on Earth. Earth will be long gone, but somewhere in a galaxy that by then will have merged with its neighbors into a single giant elliptical galaxy. The local group will have coalesced into one massive galaxy called Milkdromeda, and beyond that galaxy there will be nothing. No other galaxies visible, no cosmic microwave background, no evidence of that civilization will look up at the night sky and see only the stars of their own galaxy. They will measure the motion of those stars and find that they are orbiting the galactic center. They will see no expansion. They will have no way of knowing that the universe is billions of light years across, filled with trillions of galaxies. They will think they are alone. They will be wrong, but they will never know. And the tragedy is that we are living in the only time in cosmic history where we can know. The expansion has not yet erased the evidence. We can still see the cosmic microwave background. We can still see galaxies receding from us. We can still measure the acceleration. This is the golden age, and it is transient. Already the expansion has pushed galaxies beyond our reach. Already the number of galaxies we can ever visit is finite and shrinking. Already we are losing access to the universe beyond the local group. In a few 100 billion years, all evidence of the Big Bang and the accelerating expansion will... Future astronomers will have to take it on faith that we existed and that we saw a larger cosmos, or they will remain forever ignorant. This is not just a fact about physics. It is a fact about the nature of knowledge. The universe is not designed to be knowable. It only appears knowable to us because we happen to live at a special time, a time when the expansion is accelerating but not yet erasing, a time when the CMB is still detectable but not yet cold, a time when galaxies are still visible but not yet beyond the horizon. We are the lucky ones, and our luck will not last. To truly understand the scale of the loss, we need to talk about the cosmic event horizon. This is not the same as the particle horizon, which is the farthest distance we can see. The cosmic event horizon is the farthest distance from which light emitted today can ever reach us in the future, given the accelerating expansion. For a static universe, the event horizon is infinite. For a decelerating universe, it is finite, but for an accelerating universe, it is finite and shrinking. Currently, the cosmic event horizon is about 16 billion light-years away. That means if a galaxy is closer than 16 billion light-years, we could, in principle, send a signal that will eventually reach it. If a galaxy is farther than 16 billion light-years, any signal we send today will never catch up, because the space between us is expanding too fast. And as the acceleration continues, the event horizon shrinks. In 100 billion years, the event horizon will be about 10 million light-years away. That's the size of the local group. Beyond that, nothing is reachable. In 1 trillion years, the event horizon will be about 1 million light-years, smaller than the local group will be at that time. Everything outside our merged galaxy will be forever inaccessible. This is the cosmic solitude that awaits all intelligence. We are the only generation that will ever experience a connected universe. Our descendants, if any survive, will live in a bubble of darkness. They will have no neighbors, no external reference points, no way to measure the expansion. The universe will appear static, eternal, and empty, and that appearance will be an illusion, but it will be an illusion that no experiment can penetrate. The acceleration of the universe doesn't just change the future. It changes the very possibility of knowledge. Now, let's examine a possibility that has been gaining traction in theoretical physics. What if dark energy is not a property of space, but a symptom of something larger? String theory predicts the existence of a vast landscape of possible universes, each with different values of the cosmological constant. Our universe has a small but positive dark energy. That might be because universes with larger dark energy expand too fast to form galaxies and stars. Universes with negative dark energy collapse too quickly. We live in a universe that allows our existence because this is the anthropic principle, and it is controversial. Some physicists love it because it explains why the cosmological constant is so small. Some physicists hate it because it is untestable. If the anthropic principle is correct, then dark energy is not mysterious. It is just a coincidence. A coincidence that we are here to measure it. But that would mean that there are countless other universes out there, beyond our reach, with different physics, and we will never know. The acceleration of our universe is not just a fact about our cosmos. It might be the reason we exist at all. Without acceleration, the universe would have recollapsed or expanded too slowly to form structure. The acceleration we discovered in 1998 might be the same acceleration that made life possible. That is a profound and humbling thought. The universe is accelerating for a reason. The reason might be that we are here to ask the... Before we move to the final section of tonight's journey, let's summarize what we know. The universe is expanding. The expansion is accelerating. The acceleration is driven by dark energy, which makes up about 68% of the universe. Dark energy behaves like a cosmological constant, but we don't know if it is truly constant. The ultimate fate of the universe depends on the equation of state of dark energy. If it is exactly -1, the universe ends in heat death. If it is less than -1, it ends in a big rip. If it is greater than -1, the expansion could eventually slow or reverse. Current data favors heat death, but does not rule out the big rip. We are living in the golden age of cosmology, when we can still see the evidence of the Big Bang and the accelerating expansion. Future civilizations will not have that luxury. The universe is not just expanding, it is erasing its own history. And we are the witnesses. We are the ones who get to see the full grandeur of the cosmos before it fades. That is a responsibility. And it is terrifying. We have 52 minutes exactly. Let me now bring this to the conclusion that ties together everything we've discussed. The expansion of the universe is not a distant abstraction. It is happening right now, inside your body, inside the space between your atoms. The space between your cells is expanding. The space between the protons and neutrons in your atomic nuclei is expanding. The expansion is so weak that it is completely overwhelmed by the electromagnetic and nuclear forces that hold your body together. But the expansion is there. It is a real effect, and it is growing. As the universe ages, the expansion rate will increase. Eventually, in tens of billions of years, even the Milky Way will be torn apart by the expansion if dark energy strengthens. But if dark energy is constant, the Milky Way will survive, though its stars will all die. The expansion of space is the background against which all of cosmic history plays out. It is the stage, the director, and the ending. We cannot escape it. We cannot change it. We can only measure it, understand it, and marvel at it. And tonight you have taken that journey. You have seen the universe as it truly is, expanding, accelerating, and ultimately fading. But you have also seen that this moment, this brief window of cosmic time, is special. We are here, we are aware, and we are asking the questions that matter. That is not nothing. In a universe that is mostly empty, mostly dark, mostly cold, a tiny corner of it has woken up, and that waking up is the most remarkable thing of all. Thank you for watching. If you want to continue exploring the deepest questions of cosmology, subscribe and click the bell. The universe is waiting, and it is expanding. Continue remaining, but let's go deeper. The expansion of the universe is often visualized as dots on a balloon being inflated. That analogy is useful, but it breaks down in one. On a balloon, the surface has a center of expansion inside the balloon. The universe has no center. Every point is equivalent. The correct math is not a balloon, but a scaling factor. The distance between any 2 points grows by the same factor over the same time. This is the scale factor, usually written as A of t. When the scale factor doubles, every distance doubles. That includes the distance between galaxy clusters, the distance between atoms, and even the wavelength of light. The scale factor is the heartbeat of the universe, and we have measured its history. For the first 9 billion years, the scale factor grew as time to the 2/3 power. That's decelerating expansion, driven by matter and radiation. For the last 5 billion years, the scale factor has been growing exponentially. That's accelerating expansion, driven by dark energy. The transition happened when the universe was about 4 billion years younger than it is now. We are living in the exponential, and exponential growth is terrifying because it compounds. The scale factor doesn't just increase, it increases faster every second. In 100 billion years, the scale factor will be 10 million times larger than it is today. In 1 trillion years, it will be unimaginably large. Distances that are now billions of light years will become trillions of light years. The universe will be stretched so thin that even the most optimistic physicist would call it empty. That is the future. That is the acceleration. And we have only known about it for 25 years. Now we need to address a question that haunts every cosmologist. Is dark energy truly constant, or is it evolving? The data from the Dark Energy Survey, which mapped millions of galaxies over 5 years, puts tight constraints on the evolution. The equation of state parameter, W is -1.00 plus or minus 0.04. That's consistent with a cosmological constant. But consistency is not. The error bars allow W to be -1.04 or -0.96. That difference might not sound like much, but it changes everything. If W is less than -1, that is, more negative, then dark energy is phantom energy. The density of dark energy increases as the universe expands. The repulsion grows stronger over time. The big rip becomes inevitable. If W is greater than -1, closer to 0, then dark energy is quintessence, a dynamic field that slowly rolls down a potential. The expansion could eventually slow, stop, or reverse. The difference between these two scenarios is the difference between a violent end and a slow fade, the difference between the universe tearing itself apart and the universe cooling into silence. We do not know which one is true because our measurements are not yet precise enough. The next generation of surveys, the Rubin Observatory, Euclid, Roman, will measure W to within 1%. By 2035, we will likely know whether the universe ends in fire. But until then, we live with uncertainty. The acceleration of the universe is not a solved problem. It is an open question, and the answer will determine the fate of everything. Let's take a moment to appreciate the instruments that gave us this knowledge. The Hubble Space Telescope measured distant supernovae with exquisite precision. The Wilkinson Microwave Anisotropy Probe and the Planck satellite mapped the cosmic microwave background, revealing the imprint of dark energy on the early universe. The Sloan Digital Sky Survey mapped millions of galaxies, showing how dark energy suppresses the growth of large-scale structure. The Dark Energy Survey used a 570-megapixel camera on a 4-meter telescope in Chile to observe 300 million galaxies. These instruments are the result of decades of work by thousands of scientists and engineers. They cost billions of dollars. They required international cooperation on a scale that rivals the large and they have given us a picture of the universe that is precise to within a few percent. We know the age of the universe, 13.8 billion years, plus or minus 37 million years. We know the expansion rate, 67.4 kilometers per second per megaparsec, plus or minus half a kilometer. We know the density of dark energy, 6.6 times 10 to the minus 27 kilograms per cubic meter. That number is small, but it is not zero, and that non-zero value is the mystery. Why is dark energy not zero? Why is it not huge? Why is it exactly the value that allows galaxies to form? These are not idle questions. They are the questions that will drive cosmology for the next 50 years, and the answers will come from the same kind of hard, patient, collaborative science that gave us the acceleration in the first place. I want to pause here and talk about when Edwin Hubble discovered the expansion in 1929, he was using the 100-inch telescope at Mount Wilson Observatory. He measured the distances to galaxies by observing Cepheid variable stars. He compared those distances to the redshifts measured by Vesto-Slipher. The result was a straight line, velocity equals distance times a constant. The universe was expanding. Hubble himself was cautious. He did not claim a Big Bang. The expansion could have been a local effect, but within a decade the evidence was overwhelming. By the 1960s, the discovery of the cosmic microwave background sealed the case. The universe began in a hot, dense state. It has been expanding ever since, but for 60 years after Hubble, everyone assumed the expansion was slowing down. Gravity was the only long-range force. Gravity pulls things together. The expansion must decelerate. That assumption was so deeply ingrained that when the supernova team saw acceleration, they thought they spent months checking their calibration, their photometry, their understanding of supernova physics. They looked for dust that might dim the distant supernovae. They looked for evolution in the supernova properties. They did everything they could to kill the signal. The signal would not die. The universe was accelerating. It took years for the community to accept the result, and when they did, it changed everything. The Nobel Prize was well deserved. But the story is not over. The acceleration is real. The cause is unknown. That is where we stand tonight, at the edge of knowledge looking into the dark. Now, let's examine the most extreme possibility, the Big Rip. In this scenario, dark energy is phantom energy with W less than -1. The density of dark energy grows without bound as the universe expands. The repulsive force becomes infinite in finite time. The end is not a slow fade, but a catastrophic tearing apart. The timeline is calculable. If W is -1.2, the Big Rip happens in about 100 billion. If W is -1.5, it happens in 20 billion years. If W is -2, it happens in less than a billion years. Current constraints allow W as low as -1.04. That would push the Big Rip to several hundred billion years. That is still far in the future, but it is not infinite. The end is on the cosmic calendar. In the final months before the Big Rip, the Milky Way would be torn apart. Stars would become unbound from their galactic orbits. They would drift into the void. In the final days, solar systems would disintegrate. Planets would fly away from their stars. In the final hours, Earth would explode, not because of any internal pressure, but because the expansion of space would overcome the electromagnetic force holding the planet together. In the final seconds, atoms would be ripped apart. Protons and neutrons would separate. In the final instant, the fabric of space-time itself would be destroyed. This is the Big Rip. It is a valid solution to Einstein's. It is not ruled out by current data, and it is the most violent end imaginable. But we need to be clear, the Big Rip is not the leading theory. The leading theory is still the cosmological constant and the heat death. The Big Rip is a possibility on the tail of the probability distribution. But it is a possibility that we cannot ignore. The acceleration of the universe might be the engine of our ultimate destruction. Let's contrast the Big Rip with the heat death. In the heat death, the universe expands forever, but gently. The expansion rate approaches a constant. The universe becomes cold, dark, and dilute. There is no cataclysm. There is no explosion. There is just the slow, inevitable running down of every gradient. Stars exhaust their fuel. They become white dwarfs, neutron stars, and black holes. Those remnants cool over trillions of years. Black holes evaporate over googles of years. The universe becomes a thin soup of photons, neutrinos, electrons, and positons. The temperature approaches absolute zero. Entropy approaches its maximum. Nothing interesting ever happens again. The heat death is the most likely outcome according to current data. It is also the most depressing, because it means that all of the complexity, all of the beauty, all of the struggle and joy and suffering of conscious life is just a temporary fluctuation in a system that is ultimately headed for equilibrium. The universe does not care about us. It does not care about galaxies or stars or planets. It is just following the second law of thermodynamics. The acceleration of the universe is a symptom of that law. Dark energy is the mechanism that ensures the universe reaches maximum entropy. And we are living through the brief moment when entropy is still low enough for complexity to exist. That moment will end. The acceleration will continue, and the heat death will come. That is the cosmic narrative. That is the story of the universe, from hot to cold, from dense to dilute, from ordered to disordered. But is that really the end? Some physicists have proposed that the heat death might not be the final state, because quantum mechanics allows fluctuations. In a universe that is infinitely old, even the most improbable fluctuations will eventually occur. A random quantum fluctuation could create a new Big Bang, a new universe from the vacuum. This is the idea of eternal inflation, or of a cyclic universe. The acceleration of our universe would eventually be reversed by a fluctuation, but the timescales are staggering. The recurrence time for a fluctuation that creates a universe like ours is 10 to the 10 to the 120 years. That number is so large that it makes the age of our universe look like a rounding error. It is effectively infinite. So while the mathematics allows recurrence, the physics says it will never happen in any meaningful sense. The acceleration of the universe is not a cyclic phenomenon. It is a one-way street. Accelerating phase, it never comes back. The evidence is the cosmological constant. If dark energy is truly constant, the expansion will continue forever. There is no known mechanism that can turn a positive cosmological constant into a negative one. There is no known mechanism that can reverse the acceleration. The universe is accelerating. It will continue to accelerate. And that acceleration will eventually erase all evidence of the Big Bang, all structure, all complexity. The only remaining question is how fast the erasure happens. The heat death is slow. The Big Rip is fast. Either way, the universe is accelerating toward an end. That is the truth, and it is terrifying. Now, I want to address a subtle point that is often missed in popular discussions. The expansion of the universe does not affect bound systems. Gravity is much stronger than dark energy on the scale of galaxies, solar systems, planets, and people. The Andromeda Galaxy is moving toward us. The expansion is not pulling your atoms apart. The reason is that dark energy has a very low energy density. It takes enormous volumes of empty space for its repulsive effect to accumulate. A cubic meter of empty space contains the equivalent of about 6 hydrogen atoms in dark energy mass. That's tiny. The gravity of the Earth is about 10 to the 29 times stronger than the repulsion of dark energy on the same volume, so bound systems are safe. They will remain bound forever as long as dark energy is constant. But if dark energy grows with time, if it is phantom energy, then eventually the repulsion will overcome gravity even on small scales. That is the Big Rip. So the safety of bound systems depends on the nature of dark energy. If dark energy is constant, you are safe. Your atoms will remain together. Your body will not be torn apart. The universe will just get colder and emptier. If dark energy is phantom, then nothing is safe. Not galaxies, not stars, not planets, not... Everything will be torn apart. The acceleration of the universe is not a gentle breeze. It is a potential hurricane. And we don't know which one we're in. We only know that we are moving, and the motion is speeding up. Let's turn to the observational legacy that will decide this question. The Euclid mission, launched in 2023, will survey 1/3 of the sky, observing billions of galaxies out to 10 billion light years. It will measure the shapes of galaxies to detect weak lensing, the subtle distortion of light by dark matter. It will measure the distribution of galaxies to detect baryon acoustic oscillations, ripples in the early universe that serve as cosmic rulers. From these data, cosmologists will reconstruct the expansion history of the universe with unprecedented precision. The Roman Space Telescope, planned for the late 2020s, will do similar work with even larger field. The Dark Energy Spectroscopic Instrument, already operating in Arizona, is measuring the redshifts of 35 million galaxies and quasars. These experiments are not cheap. They are not easy. They require hundreds of scientists and engineers working for a decade or more. But they are necessary, because we cannot answer the question of dark energy without data. The theory is too flexible. The cosmological constant is a single number, but quintessence has many parameters. Phantom energy has others. Only observations can distinguish between them, and those observations are underway. Within 10 years, we will know whether dark energy is constant or dynamic. We will know whether the universe ends in heat death or big rip. We will know the fate of the cosmos. That is not hyperbole. That is the timeline of modern cosmology. We are living through the era when these questions are being answered. The acceleration of the universe is no longer a mystery. It is a measurement. And the measurement is getting better every... There is a philosophical implication of the accelerating universe that is rarely discussed. The existence of dark energy means that the universe is dominated by a repulsive force. That repulsive force is smooth and uniform. It has no structure. It is the same everywhere. This means that the universe is not only expanding, but also becoming more featureless. The large-scale structure, the cosmic web of galaxies and voids, is being smoothed out. The voids are growing. The filaments are thinning. In the distant future, the cosmic web will disappear. The universe will become a uniform, featureless expanse of dark energy with a few isolated bound systems floating in the void. The universe is losing its texture. It is becoming simpler, and simplicity, in physics, is associated with high entropy. The universe is moving toward maximum entropy. That is the second law. But the second law is usually discussed in terms of gases in boxes. It is not usually discussed as the fate of the cosmos. Yet that is exactly what the accelerating The universe is a closed system. It is expanding. It is cooling. It is becoming more disordered. The acceleration is the engine of that disorder. Without acceleration, the universe might have recollapsed, resetting the entropy, but with acceleration there is no reset. There is only the slow, irreversible march toward equilibrium. That is the deepest meaning of dark energy. It is the reason the universe has a future, and that future is cold, dark, and empty. The acceleration of the universe is not just a fact about cosmology. It is a fact about the arrow of time. It tells us that time is not cyclic. It is linear. It runs from hot to cold, from ordered to disordered, from structure to uniformity. And it will never run backward. Now I want to bring this back to the human scale. You are sitting wherever you are, watching this video. The room around you has air molecules moving at hundreds of meters per second. Those molecules are colliding with your skin, transferring the sun at 30 kilometers per second. The sun is orbiting the galaxy at 220 kilometers per second. The galaxy is moving through the local group at hundreds of kilometers per second, and the local group is being carried away from distant galaxies at thousands of kilometers per second, accelerating all the time. You are stationary in your chair, but you are also moving faster than any bullet ever fired. You are part of the cosmic expansion. You always have been, and there is nothing you can do to stop it. That is the reality of living in an accelerating universe. The motion is invisible. It is undetectable without telescopes, but it is real, and it is relentless. Every second that passes, the volume of space you can ever reach gets smaller. The number of galaxies you can ever visit gets smaller. The universe is not just expanding away from you, it is expanding away from your future. The children you might have, the civilizations that might follow, they will inherit a universe that is smaller, emptier, darker. The acceleration of the universe is the great thief. It steals the cosmos from our descendants, and we are the last generation that will ever see the full glory. That is not a reason for despair. It is a reason for wonder, because we get to see it. We get to know, we get to understand, and that understanding is the most precious thing we have. Let's look at the numbers one more time. The Hubble constant is about 70 kilometers per second per megaparsec. That means the expansion doubles the distance between us and a distant galaxy in about 10 billion years. That is longer than the age of the universe, so the expansion hasn't doubled any distance yet. But because the expansion is accelerating, the doubling time is getting shorter. In the future, the doubling time will become much smaller. Eventually, if dark energy is constant, the expansion will become exponential. The doubling time will approach a constant of about 17 billion years. That is still long, but it means that every 17 billion years, the distance between well-separated galaxies doubles. After 100 billion years, distances will have doubled about 6 times. That's a factor of 64. After 1 trillion years, distances will have doubled about 60 times. That's a factor of 10 to the 18. Distances that are now billions of light years will become sextillions of light years. The universe will be incomprehensibly vast and incomprehensibly empty. The acceleration doesn't seem fast now, but in the long run, it is devastating. Exponential growth always wins. That is the lesson of compound interest, of population growth, of nuclear chain reactions, and it is the lesson of dark energy. The universe is on an exponential curve. We are at the beginning of that curve. It seems gentle. It is not. It is the most powerful force in the cosmos, and it is. I want to share a final piece of data that puts the acceleration into a human perspective. The Voyager spacecraft, launched in 1977, are now more than 22 billion kilometers from Earth. They are moving at about 17 kilometers per second, relative to the Sun. That is fast. But the expansion of the universe at that distance is negligible. The expansion is only significant on scales of hundreds of millions of light years. That means the acceleration of the universe is not a practical concern for any human endeavor. It will not affect space travel within the galaxy. It will not affect the orbits of planets. It will not affect the lifetime of the Sun. The acceleration matters only for the largest scales, the scales of cosmology. It matters for the ultimate fate of the universe. But it does not matter for your life, or your children's lives, or the lives of anyone for billions of years. That is both comforting because we don't have to worry about the big rip tomorrow. Terrifying because it means the acceleration is patient. It will wait. It will outlast every star, every galaxy, every black hole. It will still be there when the last proton decays. It is the background against which all of cosmic history plays out, and it is accelerating. The universe is not winding down, it is speeding up, and that speed will eventually erase everything. That is the truth. That is the science, and that is where we must leave it. Before we conclude, let's address a common misconception about dark energy and the fate of the universe. Some people hear acceleration and think the universe will expand so fast that galaxies will break apart. That is not correct for constant dark energy. In constant dark energy, the acceleration is only noticeable on scales where gravity is negligible. Galaxies are held together by gravity. They will not break apart. The Milky Way will survive, though it will merge within. The stars will die, but the galaxy will remain bound. The local group will remain bound. Everything outside the local group will recede to infinity. So the universe of the distant future will consist of a single giant elliptical galaxy containing perhaps 10 trillion stars, all dead, surrounded by an infinite void. That is the fate if dark energy is constant. If dark energy is phantom, then everything breaks apart. Those are the two scenarios. Current data slightly favor constant dark energy, but do not rule out phantom. The difference between the two scenarios is the difference between a lonely but intact remnant and total disintegration. Both are bleak, but they are different kinds of bleak. One is the bleak of silence and darkness. The other is the bleak of violence and destruction. Which one do you prefer? It doesn't matter. The universe doesn't care. It will do what it does based on the physics. Our job is to measure that physics, to understand it, and to accept it. That is the role of science, not to comfort, but. Now, let's conclude this 52-minute journey. We started with a simple fact: the universe is expanding. We learned that the expansion is accelerating. That acceleration is driven by dark energy, a mysterious force that makes up 68% of the universe. We explored the two possible fates, the heat death and the Big Rip. We examined the evidence from supernovae, the cosmic microwave background, and large-scale structure. We discussed the instruments that gave us this knowledge and the scientists who made the discoveries. We considered the human meaning of an accelerating universe, the cosmic isolation of future civilizations, the erasure of knowledge, the ultimate fate of all structure. We confronted the terror of exponential growth and the patience of dark energy, and we arrived at a conclusion. The universe is accelerating. It will continue to accelerate, and that acceleration determines the future of everything. This is not speculation. This is the data is clear. The expansion is real. The acceleration is real. Dark energy is real. We do not know its nature, but we know its effect, and that effect is the dominant force in the cosmos. It has already determined that we will never reach the majority of galaxies in the universe. It has already determined that future astronomers will see only a void, and it has already determined that the universe will end not with a bang, but with a whimper, or a rip. That is the story of the accelerating universe. It is the story of our cosmic loneliness, our temporal privilege, and our ultimate insignificance. But it is also the story of our awe, our curiosity, and our courage to look into the dark and ask why. I want to end with a quote from the physicist Richard Feynman. He said, "The universe is not only stranger than we imagine, it is stranger than we can imagine. The accelerating universe is stranger than we imagined. Dark energy is stranger. The fact that we exist at this exact moment, able to see the evidence, is stranger than we imagined. And the fact that we have figured it out, not completely, but substantially, is a testament to the power of the human mind. We are small, we are fragile, we are temporary, but we are also curious. And that curiosity has allowed us to see the largest structure in the universe, the expansion of space itself, the acceleration that will determine the fate of all things. That is not nothing. That is extraordinary. So tonight, when you look up at the stars, remember that they are moving away from you. Not because of any failure on your part, but because the universe is expanding. And the expansion is accelerating. And you are living through the only time in cosmic history when you can know that. That makes you special. That makes this moment special. And that is the truth about the accelerating universe. Thank you for watching. If you made it this far, you are a true explorer. Like, subscribe, and stay curious. The universe, and it is expanding faster every second. One final note before the screen fades. The acceleration of the universe has a name, dark energy, but names are not explanations. We do not know what dark energy is. It could be a cosmological constant, a quantum field, a modification of gravity, or something entirely unexpected. The discovery of dark energy in 1998 was the beginning of a new era in cosmology. We are still in that era. We are still learning. The next decade will bring new data, new theories, and possibly new surprises. Dark energy might not be constant. It might evolve. It might couple to dark matter. It might decay into radiation. It might be the key to unifying quantum mechanics and gravity. We do not know, and that ignorance is not a weakness. It is an invitation to explore, to question, to measure, to think. The accelerating universe is not a closed book. It is an open question, and you are part of the generation that will answer. That is the reality of living now. So go out, learn, ask. The universe is expanding, and so are we.